welcome back to class. So as I warned you last time, we are going to move quickly in this course. If I didn't warn you last time, I'm warning you now. We're going to move quickly in the course, which is one reason why I'm recording the sessions when I remember to. And we're going to start today by talking about chapter 1 in your textbook. We're going to talk about all of 1.1 and hopefully most of 1.2 and maybe even all of 1.2. Oh, I can hear it now. Are there any questions for me before we get started? All right. If you do not have a question, please make sure you're muted. You can unmute yourself, of course, whenever you have a question. And please just shout out as you have a question, because I do have the chat open and I have one eye on it. But I will get in the zone and I will miss the chat sometimes. So it's always better to ask than to just send the chat message. But I will keep an eye on the chat as best I can. Before we start in the PowerPoint, I want to remind you of some of the things that we are going to need to be working on in class. Please try to get that beginning survey done by the end of the day on Friday. And please try to get the student ethics quiz done by the end of the day on Friday. And again, the ethics statement is right there. You can take that quiz as much as you want until you get full points. There is one question I have to grade by hand because I ask you to type in your name. So, but everything else you will know. It's all true, false, and you will know if you got it right or not. Again, the presentations will always be up here. The class sessions, once they're uploaded, will always be here too. And it will sometimes take me a little bit to get them uploaded. Also, if I do get it uploaded right away, it also takes YouTube time to process it. So if like at 3:45, you click on this today, there might be a link there, but it's going to say something like this video is still processing. The other thing I want to mention is participation grades, which I don't think I've put in for us yet. They're gonna show up on your to-do list, and I don't know why, but they will. You can ignore them. If you see something on the to-do list that is just a date, like 8/27 or 8/31 or whatever, ignore that. That's your participation points that I put in. You don't have to do anything at all with it, but it shows up there for reasons that I don't know why it does, other than Canvas is special. And then again, you should also be working on your math autobiography. That will be due on September 1st. So now that I remind you of that, we can talk about reasoning. So our objectives for the first part. And so remember, here's why we're doing a lot. So this is, we'll take a stretch break for about 30 seconds partway through. This class normally meets as a 3-hour class for 55 minutes 3 times a week. We're meeting for 85 minutes twice a week, which means that whereas in a 50-minute class or 55-minute class, we might just do a section a day. Here we're doing often 1.5 sections to 2 sections a day, depending on how much material there is. So we use the entire time. And today in the first part of class, we're going to learn about inductive and deductive reasoning. And this is chapter 1, section 1 in your textbook. Let me actually pull out your textbook so I make sure that I have it. There we go. The first thing we're going to talk about is inductive reasoning. You have used inductive reasoning in the past. If you ever took a science class in high school, you used inductive reasoning. If you ever thought about what will someone else do if I do this or this or this based on my past experience, you have used inductive reasoning. In inductive reasoning, we arrive at a conclusion based on repeated observations. So in science class, you observe through the microscope. And after you make several observations, you come up with a hypothesis. I think this is what's going on. In psychology, you sort of intuitively know Maybe you know that you approach one parent differently than you approach another parent. Maybe you speak with one friend differently than another friend. And you know that based on your past observations. Those are examples of inductive reasoning. That is the scientific method. The scientific method is inductive reasoning. Some definitions. In inductive reasoning, we talk about a conjecture or a hypothesis. Hypothesis is probably what you were taught by your science teachers. The conjecture or the hypothesis is the conclusion formed as a result of inductive reasoning. That conclusion may or may not be true, right? You could create a hypothesis about something and something else happens that proves your hypothesis is actually not correct. And that's okay. That's part of the scientific method. We come up with a hypothesis and we think it's true, and maybe it is at first. But as we get other data or as we do more experiences, we realize, oh, that isn't always true. Maybe you've always approached your great Aunt Mabel in one particular way. And as long as you did this, great Aunt Mabel gave you a nice crisp $5 bill. And then all of a sudden you do something that ticks her off. Maybe you don't even know about it, but your mom squealed on you. And now great Aunt Mabel is mad and she doesn't give you that crisp $5 bill anymore. So your hypothesis is no longer true. A counterexample is more sciencey than great Aunt Mabel. A counterexample is any case where the conjecture wouldn't be true. And this would prove the conjecture to be false. So if I had a conjecture that nobody under 40 years old was ever, or was he 40? No, I'll say this. No one under 45 years old was ever elected president. The counterexample would be John Kennedy, who was under 45 at least when he was elected president. He may have been under 40. I can't remember now. So all we need in math is a single counterexample. If we ever think something is true, as long as one example can be made to show that it's not true, then it's not true. So it's kind of all or nothing. You might have heard an expression, the exception proves the rule. As in, people often talk about this with people. Like someone might say, oh, I think that all lawyers are crooked. And someone else says, no, my best friend is a lawyer and she is as honest as the day is long. And the other person says, fine, that's just the exception that proves the rule. Well, really what that means is that's the exception that proves the rule wrong. Any exception, any counterexample shows that something is not true. So for inductive arguments, there are better ones and worse ones, or we say they could be strong or they could be weak. Here's an example of a strong inductive argument. Researchers took a random sample of 380,000 freshmen at 772 four-year colleges. Of those freshmen, 25% said that they frequently came to class without completing their required reading or assignments for class. Okay, so they did a sample, they surveyed many, many thousands of freshmen, and they came up with this result. The researchers then stated this: we, meaning the researchers, can conclude that there's a 95% probability that between 24.84% and 25.25% of all college freshmen frequently come to class unprepared. This is a strong inductive argument. Now, This has not been proven 100%. And they say that. And they give two things. There's several things here that make this strong. The two big things. The sample is random. These individuals were chosen randomly. And two, it is a very large sample. Those make strong inductive arguments. Being random and being a large number. Even beyond that, the researchers did what they should, and they said they were not saying with 100% accuracy that this is always true. What they're saying is there is a high probability or a high likelihood that this is true. And either going even further, saying not necessarily exactly 25%, but between 24.84% and 25.25%. We are 95% certain that between 24.84 and 25.25 of all freshmen frequently come to class unprepared. They are not saying it's 100%, and they are not saying it's exactly 25%. Now, there are certainly issues with this. If you were really digging into it, like you'd want to see what does frequently mean? Because frequently to me might be something different than frequently to you. Frequently to me might be twice a week. Frequently to you might be at least 4 times a week. So, and that might have been in the actual study mentioned and talked about. What the researchers did here is they used techniques from statistics. They used the technique of random sampling. And if every member of a group has an equal chance of being chosen, and if every group of a certain size has an equal chance of being chosen, we say it's a random sample. And from that, we can use the techniques that you will learn if you take statistics to make predictions for the entire population based on a random sample. If I, for example, took a random sample of students at Iowa Lakes and asked them what their favorite flavor of ice cream was, I would be, if I did it correct, if I chose the proper random sample, it was a true random sample, and if I chose even just 30 students, but more, let's say I chose 50 students or 60 students, I would probably have a relatively high probability. It might just be a 90%, but I would be able to get within a few percentage points of what the answer probably would be based on statistics. But the sample has to be random for that to work, which you will learn about in statistics if you take that course. So that would be an example of strong inductive argument. It's a random sample and it's a big sample. And then beyond that, the researchers kind of hedge their bets a little bit. They're like, we're not 100% sure, but we're 95% sure. And that's really common in research studies. They will say either 95% is the most common, but you might also see 90% or 98% or 99% or even 99.99% certainty. There are also weak inductive arguments. So here's one example that your authors of your textbook came up with. A student's weak inductive argument was about people. And specifically, they said, men have difficulty expressing their feelings. Neither my dad nor my boyfriend ever cried in front of me. Why is this a weak inductive argument? Well, for one thing, you just have 2 observations. You cannot judge an entire population, an entire group, based on just 2 observations. She has, presumably she, but whatever, has experiences with, talks about 2 observations, a sample size of 2. Her dad, I'm assuming it's her dad, their boyfriend. That's way too small of a sample size. Related to that, it's not random. These weren't people she randomly chose somehow. These are people that she knows very well, presumably. And so because the sample isn't random and because it's not large enough, we cannot say it represents all men with any type of accuracy. So her hypothesis might be true. We can't say whether her hypothesis is true or not, though. Now, if instead she would have surveyed 100 males chosen at random, and even just something like true or false, you have difficulty expressing your feelings. That's not a great question to ask. But if from that she said, oh, I did this survey and 60% of the respondents said yes, they had difficulty expressing their feelings, then maybe her hypothesis, there would be support for it. But as it is right here, there isn't. This is a weak inductive argument. So we do these things all the time in daily life, right? This person has that opinion about this group based on their experiences with their dad and their boyfriend. So we all kind of do things like this based on our experiences with certain people we know. We might make judgments about other people like them. That's not, I mean, that obviously that could be bad or it could be okay, but it's not scientifically rigorous. We can't make a good argument about it based on just such a small, unrandom sample. Now, in math, of course, we often use induction with numbers rather than other situations. And when you're looking for a pattern, you're using inductive reasoning. If you're looking for a pattern, you're using inductive reasoning. So one way we look at patterns is when we look at sequences. A sequence is simply a list of numbers. So here we have a sequence. Type in take a few seconds and then type in the chat what number you think comes next in the sequence. I see several people are saying 48. Why do you think 48 is the next number? That's right. We're adding 9 each time. 3 plus 9 is 12. 12 plus 9 is 21. 21 plus 9 is 30. 30 plus 9 is 39. So 39 plus 9, 48. So you're exactly right. That makes sense. One thing we have to do when we see a sequence like this is try to figure out how we get from one number to the next. If the numbers are getting larger relatively slowly, we would try addition. If they were getting smaller relatively slowly, we would try subtraction. If they were getting larger quickly, we would probably try multiplication. If they were getting smaller quickly, we'd probably try division. So we say here that 9 is the common difference between each pair of numbers. And so the next number in this sequence is 48 because we're adding 9 each time. So I say that's our rule. All right, very good. Thank you for participating. Thank you for typing in the chat. I do truly appreciate that. It makes me feel a little bit better about my life choices. Second example, still inductive reasoning, still looking for a pattern. In this sequence, what number comes next? And if you don't want to figure out the number, you could also in the chat just type what you think the rule is. Either one will work here. So what number would be next? Or what do you think we're doing each time here? Good. We are multiplying by 4 each time here. And so 768 times 4 is 3072. So that would be the next number here. Notice we started with the same two numbers both times. We started both times with a 3 and a 12. What this means is that if we had a sequence that was just 3, 12, blank, we don't know for sure what the next number in that sequence is. There's not enough information for us to say with certainty what it is. When we're multiplying like we are here, we call this a common ratio. So we're multiplying by 4 each time. We say the common ratio between each pair of numbers is 4. Any questions so far? All right. If you took psychology in high school or in college, or if you will take psychology in college, especially intro to psych, you might see this picture in your textbook, or your instructor might even display it. What is this a picture of? Is it a wine goblet, in other words, or a wine chalice, a fancy glass for drinking something? Or is it two faces looking at each other? When people see this in like an experiment, people usually see one thing or the other first. And so a person might see two faces, like here is the nose, and then it goes in, and there are the lips, and there we see the chin. And here's the other person's face, like we're sloping down from the forehead. Here's the nose, indenting after the nose. Here are the lips. There's the chin. So a person might see those two faces in profile, those two silhouettes in profile looking at each other. Or they might look at the white image in between and look, oh, look, that's some sort of glass or goblet or chalice or something. Some people immediately see one or the other. And some people then, once both of those are told, can sort of go back and forth and say, oh yeah, I get that. I can see that it could be either thing. Some people, just because of the way their brains are wired, can't do that. They only see the faces, or they only see the goblet, even if you trace the other stuff. And that's okay. There's nothing wrong with that. It has to do with with Gestalt psychology, which looks at the whole and the parts of the whole and stuff like that. We use this here to show that for inductive reasoning, there could be more than one solution. And so sometimes if there's more than one solution, you just need to explain why you think that's the solution. But if you want someone else to figure it out, you have to give them enough data for them to get there. So let's look at this sequence. 2, 4, blank. What could go next there? 6 could go next. 8 could go next. 16 might go next. We don't have enough information here unless we're going to justify our reasoning. And we could do that sometimes. Like we could say, I think we're adding 2 each time, so the next one's going to be 4. I think we are multiplying each time, so the next one's going to be 8. I think we're doing something else, so it's going to be something else each time. So usually for a sequence, we want there to be at least 3 numbers listed. And if the sequence is complicated, we might need even more than that. And some sequences do get complicated. And here's a slightly more complex sequence I want you to look at. And type in the chat when you have a guess of what number comes next in this sequence. And there are no typos here. There will sometimes be typos in the PowerPoints. I'm aware of that. And please tell me if you think there is one. It won't offend me. But there is not a typo here. Very good. Why 34? That's right. We're adding each number together. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13, et cetera, et cetera. 13 plus 21 is 34. Then we take 34 plus 21 and get 55. I'm doing that right in my head, and so on and so forth. Does anyone know what this type of sequence is called? The type of sequence where we're adding numbers together to get the next number is called a Fibonacci sequence. And Fibonacci was an Italian mathematician who, we can't really say he invented this sequence, but who sort of came across it and popularized it through his writing. And this is not the only sequence. This is the true Fibonacci sequence, but we could make other similar sequences. Like we could do 4, 6, 10, 16, 26, 42, for example. 4 plus 6 is 10, 6 plus 10 is 16, 16 plus 26 is 42, 42 and 26 is 68, and we could keep going. That's a similar type of sequence. And sometimes we call all of those types Fibonacci sequences, but this is the true one. And it turns out that the Fibonacci sequence is actually found quite a bit in nature. Your textbook talks about it a little bit here and there. And the patterns of things in nature, like certain flowers, and I can't remember if it's the spiral in a sunflower, it's how the petals are arranged on a rose or something else, but for some flowers, like it sort of follows this sequence where we first have one petal, and then we have another one, and then we have 2, and then we have 3, and then we have 5, and then we have 8, and then we have 21. So we get the Fibonacci sequence is found in different forms in nature quite a bit. Or Fibonacci style sequences in other cases. So we looked at 3 sequences that all involve numbers, but not all sequences have to involve numbers. Here we have one that involves shapes, patterns. So our instructions here say, describe 2 patterns in the sequence of figures and use the pattern to draw the next figure. It's similar, Carson, to the golden ratio in that both are found in nature to certain extents. But other than that, they are not. I'm trying to make sure this is a true statement. I think that is the only thing they have in common. They just are things that happen to be found. But actually, I'm going to go back here because I want to see this for a second. We'll go back. But I might be wrong. I don't want to lie to you. So it might be that if you look at the ratios here, that the ratios approach the golden ratio. So I just did some division here. I can't remember what the value of the golden ratio is because I can't. But notice if you take two numbers that are next to each other in the Fibonacci sequence, so like 34 divided by 21, we get 1.619. 21 divided by 13, we get 1.615. And so, and that pattern continues. We see down there 55 divided by 34. So those numbers certainly appear to be approaching a certain number, which might be the golden ratio. 293, which is on 293 or 298 of your textbook, I think. 293, golden ratio, golden ratio, golden ratio. Which is 1.618. So yes, if we were to take the Fibonacci sequence out, if we were to continue it, the common ratio between each two pairs do approach part of the value of what's called the golden ratio, which is used. It's still used a lot in like graphical design of what's supposed to look like a pretty rectangle. The golden ratio does not appear in nature as much as it sometimes is alleged to appear in nature, but it is there somewhat. Good question. Yes, so our next shape is going to be a circle, obviously with the X in it. Notice my beautiful circle there. Not deformed at all, an actual circle like that. And then how about the shapes? How are the shapes inside moving? What's going to be here in this? How many circles, if any? How many small circles? How many dots are going to be here? You probably can't see where my mouse is. How many small circles are going to be here in this segment? There's going to be one small circle in this segment here. So we're going to have 1, 2, 3. It's actually going to look exactly like our first shape again. So what's happening are two things here. We're going back and forth, circle, square, circle, square, circle. And then the other thing is that our small circles are rotating, and they are rotating each time, but they're rotating counterclockwise by 90 degrees each time, 1/4 of a turn in the circle. And so by the time we have 4 rotations, we've gone around 360 degrees. We are back to where we started from. So here's what it actually looks like drawn appropriately, as opposed to my lovely mouse drawing. So we can also use patterns of induction to find visual sequences like this. Other types. Here we have a sequence. What do you think the next entry in this sequence might be? F. This appears to be letters of the English alphabet, which is also called the Roman or the Latin alphabet. So it would make sense the next entry would be F. Now, for a problem like this, we can't be 100% sure. It might be, maybe these are the titles of books I have on my bookshelf, and it happens to be the first letter. So the first one is this, starts with an A. We have Animal Farm, and then I have Beowulf, and then I have Canterbury Tales, and then I have Dandelion Wine, and then I have some book that starts with an E. And then my next book might actually be Lord of Light. So really the next entry is an L. We don't know 100%, but it would make sense that our next entry would be an F. Here's a little trickier one. How about this sequence? What would the next entry be here? Excellent. Here, our sequence is the consonants, again, in the English or Roman or Latin alphabet. So we have B, C, D, no E, that's a vowel, F, G, H, no I. So our next letter would be J in the contemporary English alphabet. Let me give you a bonus one since you're doing so well. That's supposed to be an M. So we have J, F, M, A, M, J, J, A, S, O, N. Why D, Owen? December. These are the months of the year. Why S? That's fine, Dayton. For Saturday, days of the week. All right, one more, and then we will move on. Good, Carson. Why E? For 8. Excellent. All right. So we use induction for these other type of brain teaser ones as well. Again, we can't be 100% sure because it could be that these letters also are, maybe they're the first letter in words, the first letter of each sentence in a book or something else like really weird and bizarre. But we're always making just a guess with induction reasoning. We're making an educated guess. We think this is the pattern. The other type of reasoning is deductive reasoning. In deductive reasoning, we prove a conclusion from one or more general statements. We're using logic to prove something. So for deductive reasoning, something is always true. It's not just true based on our experiments, or it's not just true based on our observations. It's going to be true for everything. For any number that might get plugged in there, it would be true. Whether the number was 7 or 25 or 82 million or 0.3 or -17, it's still going to be true. And if a conclusion is proven to be true using deductive reasoning appropriately, correctly, we call that a theorem. Not a theory, a theorem. If you did proofs in high school geometry class, you did deductive reasoning. Even if you took certain English classes in high school, it's like when I taught high school English, one of the things I got to teach because God likes to punish me was AP language and composition. And one of the things we talk about in AP language and composition is rhetoric. And part of rhetoric are ancient Greeks who did things like all humans are mortal. Socrates is human. Therefore, Socrates is mortal. And so there's those types of things are deductive and inductive reasoning. Proofs were kind of one of the things I actually liked in high school math. One of the few things. I did not like them in college geometry though, so something my mind changed over time. May have been the instruction involved, however. We aren't going to do proofs in this class. Fear not if you don't like them. My apologies if you do like them. But we are going to use deductive reasoning because that's what mathematicians prefer. First, an example without numbers. So two people are playing Scrabble or Words with Friends, whatever. And one player says to another, you have to remove those 5 letters, you filthy cheater. You can't use Texas as a word. And so why is this? Well, we can look at deductive reasoning based on the rules of Scrabble. Our general statement is what we start with in deductive reasoning, is that all proper names, like Texas, are prohibited in Scrabble. Then our specific sort of implementation of that general statement, Texas is a proper name. And then our conclusion, therefore, Texas is prohibited in Scrabble. So get those letters off the board, or just reshuffle them and get taxes instead. That's everyday life deductive reasoning. It's using logic from a general principle to the relevant conclusion. And we use deductive reasoning based, again, it's still based on our experiences sometimes to make sense of the world. So we're going to look at these two things compared to each other. So we're going to start with inductive reasoning, and we're going to have a series of steps. So the rules are select a number, and we see there's 3 different examples here. We'll go through each of them. First, multiply the number by 6, and then add 8 to that product, and then divide that product by 2, and then finally subtract 4 from the quotient. So we have one example here is 4. So 4 times 6 is 24. 24 plus 8 is 32. 32 divided by 2 is 16. And 16 minus 4 is 12, which is our answer. So we'll do the same thing with 7. 7 times 6 is 42. 42 plus 8 is 50. 50 divided by 2 is 25. 25 minus 4 is 21. We'll do the same thing with 11. 11 times 6 is 66. 66 plus 8 is 74. 74 divided by 2 is 37. 37 minus 4 is 33. I'll do one more here before I ask you to see if you see a pattern. I'll ask in a second, in a minute. First, we'll do one more example. Actually, one of you, give me a number that's less than 20, please. 15, thank you. 15 was the first one I saw, so sorry, so we'll do 15. So 15 times 6 is 90, I think. Feel free to check my work as I go to see if I get any of these wrong, which is entirely possible. And see if I can find where my pen is. There we go. So 15 times 6 is 90. 90 plus 8 is 98. So let's see, we start with 15. 98 divided by 2 is 49. And 49, I did something horribly wrong here. Is 15 times 6 90? Yes, 90 plus 8 is 98. 98 divided by 2 is 49. Oh no, I did it right, sorry. Okay, I'm looking at 2 things at the same time. That's right. So my answer is 45. That is correct. That is my right answer. Any ideas of what our pattern is here? I'll do one more. I'll do 14 since that one actually showed up first. 14 times 6, I'm going to cheat. and use my calculator off screen. 14 times 6 is 84. I should have been able to do that in my head, I know, but it's late. Well, it's late for me. It's been a long day. 84 plus 8 is 92. 92 divided by 2 is 46. And 46 minus 4 is 42, which is correct. They are all divisible by 3. That's right. And so our rule is here, we're taking this number and we're multiplying it by 3. 4 times 3 is 12. 7 times 3 is 21. 11 times 3 is 33. 15 times 3 is 45. 14 times 3 is 42. If I had done 19, it would be 19 times 3 is 57. If I would have done 6, 6 times 3 is 18. But for mathematicians, just doing a bunch of examples isn't enough, because just from this, we don't know that this is always true. Maybe this isn't true if I chose 0. Maybe this wouldn't be true if I chose -1. And so we have to use deductive reasoning. That's what we'll do on the next slide. When we use deductive reasoning, we often use the letter n as our variable. I know in algebra we usually use x, but when we're talking about what's called number theory, we usually use n for number. And so our first step is, and this is going to look kind of similar to proofs. Our first step is to select a number, and we call that n. And then if we look back here, so again, here's what we're doing. We're taking this stuff right here, and we're going to translate this into mathese. We're going to go from English to math. Next, we multiply the number, that should say by 6. And so in algebra, we call that 6n, right? That means 6 times n. Then we add 8 to that product. So that's 6n plus 8. And we divide that sum of 6n plus 8 by 2. So we do this by breaking it apart, making it 2 fractions. We get 6n divided by 2, that's 3n. And we get 8 divided by 2, that's 4. So 6n plus 8 divided by 2 is 3n plus 4. And then from that quotient, we subtract 4. So 3n plus 4 minus 4 is 3n. And that was our hypothesis. We multiply whatever the number is by n. And so what we have then proven here, what we've shown here, is that this is going to work for any number. So if I took, let's say instead of a whole number like we've been doing, I took -1.23 as my n. So first, I multiply that by 6. And then I add 8 to that. And then I divide my answer by 2. And then I subtract 4 from that. And I get -3.69. And that should be the same, and luckily it is, as -1.23 times 3. -3.69. So what we get by using deductive reasoning, this is why, one of the reasons why it's used in geometry, is that what we're doing is we're proving something always works no matter what the number is. We could do this with pi. We could do this with the square root of 17. We could do this with a fraction. We could do it with a really big number, with a really small number. This will always be, whatever we start with, we'll end up with 3n. If we start with pi, we'll end up with 3 pi. If I started with -20, I'll end up with -60. If I start with 1 billion, I'll end up with 3 billion. Doesn't matter what the number is. And that's what we want, because sometimes in math, we'll see things that sometimes work. Like maybe it only works for positive numbers, or maybe it only works for even numbers, or maybe it only works for multiples of 16. But what we usually want is something that will work for all numbers. numbers. Now, sometimes we do need to narrow it down. We will say this is designed to work only for integers or only for natural numbers or stuff like that. But it's still for every example of those. And that's the power of deductive reasoning. So we use inductive reasoning, including in math, to make hypotheses. We often will make that inductive hypothesis before trying to prove it deductively. Because as you might know from high school geometry or other classes, it can be challenging to do proofs, especially if they're not guided proofs, if it's just you out in the mathematical wilderness. I did not enjoy my graduate level proofs class at all, unlike high school geometry. Having a hypothesis first helps us. It helps sort of focus us. It helps us narrow the possibilities. And we use deductive reasoning in math or in logic to show that something is always true, not just sometimes. Again, in math, just giving lots of examples isn't enough, because just one counterexample can prove that the rule is wrong. Again, the exception proves the rule really means the exception proves the rule is incorrect. Any questions so far? All right, this is your time to stretch. Take 10 seconds or so. And if you want, I'm not going to make you. If we were in class, I would make you. I'm not going to make you from your home or whatever, but stretch, sigh with your mic off, scream at the top of your lungs if you want. Doesn't matter. Take 10 seconds or so. Get some blood flowing. Get refocused. We're on the home stretch. We're more than halfway done. The second thing we're going to talk about in class today is section 1.2. And we're specifically going to talk about estimating and rounding. And I know that you've been taught how to do both of these things before, and I'll talk about why I'm spending your valuable time doing it right now. If we have time, we'll also talk about modeling. I am probably going to give you some unofficial homework, which is to do the reading graph stuff on your own, because I also think you know how to read a graph. So these are our 4 objectives for section 1.2. By the time either we are done or by the time you're done going over the section in your textbook, you should be able to use estimation techniques to get a reasonable answer. You should be able to round whole numbers and decimal numbers. Decimals are sometimes trickier. And then sort of on your own, you should be able to apply those estimation techniques to get information given by graphs. So about how many people prefer strawberry ice cream compared to chocolate ice cream compared to vanilla ice cream. And then if we have time, we'll do this today. Otherwise, we will take this up on Tuesday. We will talk about math models. And we're going to start with estimation. Estimation is how we arrive at an approximate answer to some sort of question. Why is estimation important? I will say when I used to teach elementary math way, way long ago, it was one of the least favorite things of my students. It was one of my least favorite things. I hated estimating. I would much rather, like I'd say, why am I estimating? Why can't I just add or subtract or multiply or whatever? The point here is really estimating is a way for you to see if an answer is reasonable or not. One of the goals we have in this particular class is that one of the things we would like for you to leave Math for Liberal Arts with is to do this, to be able to say, this seems reasonable, or conversely, this does not seem reasonable. You can use a calculator in this class. Obviously, you can do that, but we can mistype on calculators. So if my problem is 25 plus 5 and I type in this and my calculator tells me the answer is 125, I should immediately stop and ask myself, does that seem reasonable? That's a life skill. Honestly, I know life skill gets thrown around a lot, I think, but I really think it is. And it's something that does show up not just in math classes, but in other classes, but in real life too. Does this argument being made by someone, does this seem reasonable? Do these economic figures seem reasonable? Does this result I get in this experiment I'm doing in science seem reasonable? Judging how reasonable something is valuable. And it's something that if you're just trying to plow through a bunch of problems to get through them, that gets sort of skipped along the way. That's unfortunate, and it's something that trips people up in other math classes too. In statistics, one of the things we talk about in statistics is the idea of probability, how likely something is to occur. And for probability can never be less than 0, and probability can never be bigger than 1. And so if you're figuring out what is the probability that it's either going to rain or hail tomorrow, that probability is going to be somewhere between 0 and 1. But every semester, there's probably at least one student who takes a question like that and will say something like, the probability is 2.75, even though probability can't be bigger than 1. Like, it's impossible. 1 is 100%, and you can't be more than 100% likely for it to rain or hail tomorrow. And why did they get it wrong? It's not because they don't understand how to add. It's not because they're stupid in any way. It's just because we get in such a groove, we don't stop and check and think, is this a reasonable answer? So estimation helps us determine if an answer is reasonable or not. A big part of estimating is rounding. And so I'm going to spend a little time on rounding whole numbers and here's why. As I've said before, the other math classes I teach here at Iowa Lakes are finite math and statistics. And particularly in statistics, we round a lot. Most statistics answers end up being decimals that go on forever. And so the directions always say something like round to the nearest hundredth, or round to the nearest tenth, or round to 4 decimal places. If you're told to round to 4 decimal places and you round to 5 decimal places, you might think, oh, that's going to be even better. I'm being more precise, being more exact. You're not. If you're told to round to 4 decimal places, you have to round to 4 decimal places. I mean, there's reasons for that. One reason is that how many places you round something to is evidence to your reader of how accurate your answer is. But your answer can't be more accurate than your beginning measurements. So if you're measuring, if you're actually measuring something in, let's say, a science class or in a construction class, and you're measuring something to the nearest inch, let's say, of everything, and then you do something and you find out the average measurement or something, and although you're measuring everything to the nearest inch, you say, oh, the average length is blah 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 0.12405 inches. Like you're telling the average to 5 decimal places. Someone who sees that thinks you're actually measuring that precisely all the way along. So instead of measuring to the nearest inch, you're measuring along the way to like the nearest thousandth of an inch, which you're not, most likely. So if you're told to round to, say, 2 decimal places, that's exactly what you should do. And people don't always do that, which is why I've started spending a little more time in Math for Liberal Arts on, even though I know this is something you've been taught before. I know that. I taught 5th grade math. I taught rounding to my 5th graders. But if we don't use it, we lose it. And sometimes because we've had lousy teachers, and sometimes just because we forget or misunderstand, we get into bad habits. When you round a whole number is a number that doesn't have a decimal part to it. You first figure out what digit you're supposed to be rounding to, so like to the nearest hundreds or the nearest thousands or the nearest ones or units. And then you look at the digit immediately to the right of it. Those are the only 2 digits that matter. So if I have this number, that's supposed to be a 4 there. 844. There. Let's say I want to round this number to the nearest 10,000. The first thing I want to do, I'm going to kind of draw this as I go, which you do not have to do when you're doing this, is I want to find the 10,000s place. So my 10,000s place is right here. Then I want to look at the digit immediately to the right of that. It doesn't matter what any of these other digits are. Sometimes a student will look at this 7 and they will say, oh, well, that 7 really makes that 4 or 5. It doesn't. You look only at the digit immediately to the right. If the digit immediately to the right of the number you're rounding is 5, 6, 7, 8, or 9, then you add 1 to the digit that you're rounding. Otherwise, you leave it the same. Here, it's not 5 or above, so I leave that first 4 the same. And then after that number, I replace the other digits with zeros. So to the nearest 10,000, 43,844,729 to the nearest 10,000 is 43,840,000. So one common mistake that students make is they start rounding too soon. They say, oh, well, this 7 really rounds this 4 up to a 5. So this is really 850,000. It's not, I promise you. So another example. We run around 4,867 to the nearest 100. The first thing we do is we look at the hundreds place. Our hundreds place here has an 8 in it. We then look at the digit immediately to the right and only that digit. And we see, is it 5 or greater? It is. So that means I add 1 to the digit I am rounding. And I change everything else after that to a 0. So the nearest 100, this is 4,900. And obviously, if it's less than 5, now this is sometimes confusing how we say it. And I catch myself saying this too. We say we round down, but we really don't. We don't change the digit if it's less than 5. We keep it the same. So 4,847. So again, to the nearest 100. Here's my hundreds place. Here's the digit to the right. 4 is less than 5. So my 8 does not change. It stays an 8. And we get 4,800 as our answer. Any questions so far? Okay. Again, if you have a question, just shout it out. One symbol I want you to be aware of is the symbol that we read approximately or approximately equal to. And it looks a little bit like 2 tildes, one over the other. If you're typing something ever in Canvas and need to show it, you can just use the single tilde symbol to show it. But you can, if you're typing in Word or on paper, you can actually find that symbol, or writing on paper. We use this after we rounded something. So for example, you remember from high school that pi is approximately 3.14159, but we usually will round that maybe to 2 decimal places. So it's really, we would say pi is approximately 3.14. And we use this as approximately equal to symbol rather than the equal symbol, because attention to detail matters. If we say equal to, we're supposed to mean exactly equal to, not almost equal to. And equal to in real life, we sometimes do use it in those terms, like, oh, it's about that. So yeah, it's equal to that, but it's not exactly the same. And so this is the symbol we want to use. And again, there's not a keyboard symbol for that. But if you're doing something on paper, you should do the squiggle lines rather than the straight lines, or something is approximately equal to. Another example here, world population. So from a few years ago, world population was 7,058,746,857. I need to say 2 things about this before I talk more about it. Thing number one, if you're an international student, I understand that different countries have different ways of expressing large numbers. Not every language, for example, has an equivalent to the word billion in English. In fact, even in British English, using the US approach is kind of newish. Not probably new in your lifetime, but almost new in my lifetime, definitely new in my parents' lifetimes. Traditionally, this number might have been read, depending on the language, as something like 7,000 million, or sometimes a word that's called milliard was used as well. So in the US, we have millions, billions, trillions, quadrillions, quintillions, sextillions, septillions, octillions, nonillions, decillions, and many more. Whereas in other languages, when those are translated in local language, we might have, instead of billions, we might have either 1,000 millions, or we might have milliards. It might continue then, we might have then just skip billions and then go to trillions, 1,000 trillions, quadrillions, thousands of quadrillions. It varies from language to language. So both if you're an international student, or particularly if you're in something like business, you're going to go into business or economics or anything like that, are going to work with in international contexts, be aware that super large numbers are presented differently in different cultures. We're going to round, and the other thing I want to mention, I remember now, when you see population for something and you see that it's like it ends in like, oh, and there's 57 people. There is no earthly way that we know exactly how many people live on this planet. Frankly, we don't know how many people exactly live in the state of Iowa. Populations are always estimates. And demographers, which are people who study population, will pull their hair out when they see something like this, because they know that we can't be this precise with what the population is, anywhere near this precise. I just want you to be aware of that. So now that my rants are over, we will talk about rounding this to the nearest 100 million. So first, we find the 100 million place. And again, I'm underlining here. You do not have to underline it like I'm doing, but I just want to make it sort of step by step. So here's our 100 millions place. And then we look only at the digit immediately to the right. And we see this is 5 or above, which means we increase the digit in the 100 millions place by 1. And then all other digits, including that 5, we change to zeros. Another mistake that I sometimes see students make is that they will keep the other numbers the same. Like they'll keep this as 746,857. Everything becomes a 0 after the place we're rounding to. if it's a whole number. So rounded to the nearest 100 million, 7,100 million. And to a demographer, that would be a much better thing to say anyway. Maybe round to the nearest 10 million we could do as well. Now we'll round to the nearest million. So first we find the millions place. And then we find the digit immediately to the right of that. Notice it's 5 or above. And so that means our millions place goes up by 1. And everything else becomes a 0. Everything else after that becomes a 0. So 7,059,000,000. I want to give another example that sometimes trips people up. So let's say we have $43,999. I want to round this number to the nearest 10. So first I find my tens place. I see there's a 9 in it. And then I go 1 digit to the right and I look and I see this number 5 or above? Yes, it is. So I'm going to add a 1 here. What happens when I add 1 to 9? I get a 10. And what I sometimes see, and this is more in like middle school and sometimes high school, but I've seen stuff like it sometimes in college. What I'll see someone write is something like this. Which is obviously not right. So it is, as Alex said, we would write this, even though it's rounded to the nearest 10, to the nearest 10, this is going to be 44,000. Because 9 plus 1 is 10, but really what we're doing then is this becomes a 0. We add 1 here, that becomes a 0. We add 1 here. It's like we're carrying, just like we were adding like back in elementary school. We learned how to add with carrying numbers. We're doing the same thing. And so that sometimes trips people up, especially if they aren't used to it, and it will show up occasionally. Finally, we'll do it to the nearest 100,000. So we find the 100,000s place. We look at the digit immediately to the right of it. And then everything else, notice it's less than 5. So the 7 stays the same. And then everything else, whoops, that's right. Everything else becomes a 0. So 7,058,700,000. Questions? All right. The last part of rounding I want to talk about is decimals. We're going to use pi as our example. So the first 7 digits of pi, 3.141592. This is to right now 6 decimal places, 7 digits altogether, because the 3 is also a digit, of course. We want to round it to the nearest hundredth. So remember, for decimals, we have tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, and it keeps going. There is no equivalent as a 1th. Like, right, this is the ones place, and then we'd have tens, hundreds, thousands. But after the decimal point, our first term, our first place value is tenths. Again, remember, in the US, we use a period to represent a decimal, not a comma. So rounding this nearest hundredth, we're going to underline our hundredths place. It's a 4. And we look at the digit immediately to the right and only that digit. We see that's a 1. So that means we do not add 1. We keep the 4 the same. If it's a decimal, we just drop all of the other numbers. So when we round pi to the nearest hundredth, that means we should only have 2 decimal places, 3.14. Don't put zeros afterwards. If I put 3.140, I'm rounding something, not pi, but something, to the nearest thousandth. Now I'm rounding to the nearest 10,000th. Now I'm rounding to the nearest 100,000th, or to 5 decimal places. So if it's the nearest hundredth, you should have exactly 2 numbers, 2 digits after the decimal point. Here would be the nearest thousandth. We look at the thousandth digit, which here is the number 1. We look at the digit immediately to the right of it, which here is the number 5. And so in that case, we are going to add 1 to 1, and we're going to drop all the other digits. So pi to the nearest thousand would be 3.142. Questions? Okay. I want you to be really careful with this, and this is going to show up on the homework. If you are told to round something, let's say your answer to a problem is 11.6. And I tell you, round this to the nearest whole number. You'll give me this answer. If I say, round this to the nearest tenth, you will give me this answer. If I tell you, round this to the nearest hundredth, you will give me this answer. On a number line, these two are the exact same number. I know that. I'm not stupid. But this is more precise when we're dealing with rounding. So nearest tenth, nearest hundredth. And maybe you'll get an answer. Vectors 1 looks a lot like, well, let's not do 11. Let's do 15. This one says 15.0004. If I ask you to round this to the nearest whole number, you'll say 15. To the nearest tenth should be 15.0. To the nearest hundredth should be 15.00. Okay? If you are told to round something to the nearest hundredth, you should have 2 digits after the decimal point, even if they're both 0. Nearest thousandth, you should have 3 digits after the decimal point, even if they're both 0, or all 3 are 0. Okay? Questions about that? That's not super important for us, but it'll be super important for you in other math classes and other science classes, even in other like social science or econ classes. It could be important. So I just want us to be on the same page. You might also be told with a decimal problem like this that what we want to do is we want to round it to a certain number of decimal places. So if I tell you to round this to 4 places, that means you would get 3.141, and then the 4th decimal place is a 5. 9 is bigger than 5, so we get 3.1416. 4 decimal places. Usually, you might see tenths and hundredths written out as round to the nearest tenth, round to the nearest hundredth, maybe even round to the nearest thousandth. But for other decimals, it's going to be the decimal places, round to 4 decimal places, to 5 decimal places, or more. So in stats, for example, we find p-values in stats, and we always round those to 4 decimal places. Finally, for us today in class itself, using rounding when we estimate. You go to the grocery store, and here's what you've purchased. You purchased a loaf of bread for $2.59, some detergent for $2.17, a sandwich for $3.65, an apple for 47 cents, and coffee for $5.79. You go to checkout, and the clerk tells you you owe $18.67. Is that a reasonable amount? We can find this out really quickly by estimating. We're going to round each of these to the nearest dollar. So we have $3, $2, $4, $0, and $6. We're going to add these 5, 9, 0, 15. So our estimation told us our bill should be $15. The checkout clerk tells us we need to pay $18.67. Does that seem reasonable? No, they're trying to cheat us. We're going to take them down. Let's double check. You're going to put the actual values in. You're going to say, well, you rounded. Rounding is never exact, and that's true. But if we added these exact values, and we're assuming there's no sales tax, by the way, there is no sales tax. We should have been charged $14.67. They're overcharging us by $4. And so again, there's no need for you to pull out your calculator when you're at Hy-Vee or Fairway or wherever, but you certainly can estimate prices as you're going. And one way to do it is to just round to the nearest dollar. There are other ways as well. That good. The graphs and estimation stuff we are not going to go over in class. We're right on time where I want to be. What you're saying there, Julian, is sometimes true in some cases, and that's something we're going to talk about next time. For right now, though, don't do it that way. If it's 5 or above, round up, even if it's even or odd after it. And if it's less than 5, do not round up. We'll talk about that more next class, but don't do that right now. But you are right. What we're saying here, these are guidelines, not hard and fast rules, and we're going to talk about that. Thank you for that. The next slides up here are about graphs, and I'd like for you to look these over and possibly in your textbook where it talks about this. When it gets to the word modeling, I want you to stop because that's what we're going to start up on Tuesday. We're going to talk about modeling, and then we'll talk more about some of the exceptions for rounding that I want to talk about as well. So the last thing I want us to do in the 4 minutes we have left is for you to give me your attendance. So we are going to do this. Not that. Not that. Not that either. And I have a specific question I want you to answer as well. So please click on the link you see. There is your name. There is a 1 or 2 word, not sentence, word summary of class. And then if you have any questions or comments, you can also add those, but that's optional. So we have 3 minutes of class left, so that should give you plenty of time to do that officially. And then if you have any questions, please send me an email. Otherwise, I will see you on Tuesday. Have a great rest of your day. Have a great weekend and make good choices.
It says sign into a Google account. We don't have Google accounts.
If you sign into your Iowa Lakes account,
Yeah, it don't work like that.
Okay. Don't worry about it. In that case, I will look into that because
Thank you.
it should work.